What is AGB Star? An asymptotic giant branch, AGB, star represents the final luminous phase in the life cycle of intermediate mass stars, typically around 3 solar masses, lasting a few million years. Throughout a star's lifetime, it undergoes distinct stages of stellar evolution, characterized by different nuclear burning processes, temperatures, and durations. The AGB phase is distinguished by alternate burning of hydrogen and helium in surrounding shells, intense convection, mixing, and substantial mass loss. This phase is divided into 2 periods, the early AGB, EAGB, and the more significant thermal pulsing AGB, TPAGB. During the TPAGB phase, the star experiences cycles of expansion and contraction, known as thermal pulses. These pulses are driven by energy from hydrogen and helium shell burning, causing the star to expand and collapse rhythmically. As this process unfolds, the interior layers of the star are dredged up to the surface, with carbon being one of the primary elements brought outward. These thermal pulses are vital for enriching the star's atmosphere with heavy elements, contributing to the star's eventual transition into a white dwarf, while also influencing the surrounding interstellar medium through mass loss. In this phase, the AGB star exhibits significant mass loss, often leading to the formation of a circumstellar envelope of gas and dust. This period is crucial in stellar evolution, as it not only determines the star's fate but also plays a key role in enriching the cosmos with elements like carbon and oxygen, essential for forming planetary systems and life. What is the importance of AGB stars? A galaxy is composed of hundreds of billions of stars at various stages of their evolution, and the energy emitted by these stars forms the total spectrum of the galaxy. The history of star formation within a galaxy is, therefore, encoded in this integrated spectrum. By analyzing galaxy spectra, astronomers can better understand the processes of galaxy formation and evolution. This is done by comparing observed galaxy spectra to stellar population models, which are built upon detailed knowledge of stars, derived from both theoretical frameworks and observations within our own galaxy and nearby galaxies. While most stellar phases are well understood and modeled with reasonable precision, the thermal pulsing asymptotic giant branch, TPAGB, phase has been a point of contention for decades due to its complex stellar physics. Different models of stellar populations produce highly divergent predictions, particularly in the near-infrared (NIR) range, spanning 0.5 to 2 microns, where cool AGB stars are most prominent. Depending on the model, the contribution of AGB stars to the NIR emission varies significantly, from as low as 20% to as high as 80%. This inconsistency has hindered accurate determinations of key galaxy properties, such as their ages and masses, especially for galaxies around 1 billion years old, when the TPAGB phase plays a dominant role in their spectral output. What is the discovery? Earlier studies suggested that distant quiescent galaxies would be ideal candidates for investigating the contribution of thermal pulsing asymptotic giant branch, TPAGB, stars. However, these conclusions were primarily drawn from broadband photometric data, which is susceptible to degeneracies and often yields inconsistent results. This limitation made it difficult to reach a clear consensus on the TPAGB's contribution to galaxy spectra. Fortunately, the advent of the Near-Infrared Spectrograph (NIR-SPEC) on board the James Webb Space Telescope (JWST) has provided a breakthrough. NIR-SPEC is capable of obtaining high-quality spectra across a broad wavelength range of 0.5 to 5 microns, a range that captures the key absorption features associated with TPAGB stars. In a serendipitous discovery, we identified 3 quiescent galaxies exhibiting clear spectral signatures of TPAGB stars from our Cosmic Evolution Early Release Science, source, JWST/NIR-SPEC program, DD-ERS 1345, and a follow-up program, DD-2750. Among these, One galaxy, designated D36123, stood out for its exceptional brightness and the superior quality of its spectrum. This marks the first-ever detection of distinct AGB star features in distant galaxies, including prominent absorption bands associated with oxygen and carbon-rich stars, spectral discontinuities, and rare elemental features. The observed spectra reveal an array of AGB indicators, broad molecular absorption bands like TO, CN, and C2, along with more uncommon species such as VO and ZRO, all of which strongly confirm the presence and prominence of AGB stars in these distant galaxies. The detection of such features is groundbreaking, as these stars play a significant role in shaping the later stages of stellar evolution, influencing not only the luminosity and spectra of galaxies but also their chemical composition and dust production. We further compared the observed spectra with various stellar population models, each incorporating different treatments of the AGB phase. Our analysis revealed that models with a more significant contribution from AGB stars provided a much better fit to the data, suggesting that these galaxies are younger and have lower stellar masses than previously estimated. This finding has far-reaching implications for our understanding of galaxy evolution and stellar populations. The underestimated influence of AGB stars in previous models may have led to systematic errors in determining the ages and masses of distant galaxies, underscoring the need for a revision of published stellar population fitting results. The spectrum of D36123, plotted as a double histogram to illustrate the plus or minus 1 sigma noise levels, showcases the extraordinary quality of the data obtained. Numerous broad absorption features and spectral discontinuities in the near-infrared region, specifically linked to AGB stars, are clearly detected. Notably, this is the first time these molecular absorptions, such as TO, CN, and C2, have been observed in the spectrum of a distant galaxy. The presence of additional spectral features, including VO and ZRO, further highlights the significance of the AGB phase in these galaxies' spectral characteristics. An inset from the JWST's and ARCam imaging shows the compact, quiescent morphology of galaxy D36123, offering a visual confirmation of its structural properties. These results not only open new avenues for exploring the role of AGB stars in distant galaxies, but also enhance our understanding of cosmic dust production and chemical enrichment across cosmic time. What is the next? The spectrum of D36123 is, at present, entirely unique, with no known counterparts in the local universe. However, there is no indication that this quiescent galaxy is extraordinary in any particular way. It appears to be quite normal and representative of its type. To confidently rule out any unusual characteristics and to better quantify the contribution of AGB stars to galaxy spectra, as well as the diversity and intensity of the associated spectral features, a larger sample of similar observations will be essential. Indeed, even the best-fitting stellar population models currently available cannot fully capture the complexity of the spectral features we have identified in D36123. This has led us to develop the next generation of models to better account for these complexities. Fortunately, we are scheduled to obtain new observations using the JWST next year. These future observations will be invaluable in expanding our understanding of AGB stars, their influence on galaxy models, and their role in the production of cosmic dust and the chemical enrichment of the interstellar medium. By examining a broader range of galaxies, we aim to refine our models and deepen our insight into how AGB stars contribute to both the physical properties and the evolutionary processes of galaxies across cosmic time. This upcoming data will provide crucial steps toward resolving the uncertainties that currently limit our comprehension of these distant galaxies and their stellar populations.